Hello everyone. So today a new day will discuss about the concept of statistical inference. So in statistical inference we have two sub parts, that is estimation. One is estimation theory and another one is testing of hypothesis. So today in this video we'll discuss about the concept of estimation theory. So you know all the theoretical definitions. We will not discuss those definitions today. We only discuss the pure theory, pure concept of uh, estimation theory. Why we use this? What is the need behind estimation theory? So first of all, we have to know what is estimation. Why we need this? So let we have a large number of population. Let this is my population. So this is my population. This consists of n units up to capital N. So let we have three enumerators. First one name is Ram. Second one name is Abdul. Third one name is Jack. So there are three enumerators here. So these three enumerators draw samples, different samples. So let Ram takes the samples x1 up to xn. Abdul's sample values are y1 up to yn, and Jack's sample values are z1 up to zn. So now the question comes, so which sample truly represent the whole population? Because a sample definition is representative part of population. So how we know which sample will truly represent the whole population? So here the entry comes estimation theory, which set a parameter so that we can say an sample values or its estimator is a truly defines the whole population. So here the estimator is what? Let the sample values of RAM is x1, x2, xn. So let I have taken t equal to x bar, which is mean of this sample. So this can be a estimator. So let yeah, it's t1. Let I take t2 equal to s. S square, its sample mean square, sample variance, which can be a estimator. So similarly I can take here Abdul as t1. Let it be y bar, so it can be a estimator. T2 s s1 square, s2 square, it can be a estimator. Similarly here z bar, t2 equal to s3 square, so this can be also a estimator of the population. So here there are four characteristics which must be satisfied by a good estimator. So first one is unbiasedness. Second one is consistency. Third one is efficiency, and the fourth one is sufficiency. Now first of all the question comes, what is unbiasedness? So unbiasedness, let we have sample values x1 up to xn, which come from a population which we can say is normally distributed with mean mu and variance sigma square. So this is the distribution of the population. Here we have take the population 1 to up to n. So we assume this to follow the normal distribution with mean mu and variance sigma square. So here the sample drawn will also follow the normal distribution with mean mu and variance sigma square. So if the sample mean we have calculated here as x bar equal to summation xi divided by n, I equal to 1 to small n. So if the expected value of x bar gives the population mean, that is mu, so we can say our estimator is a unbiasedness, follows the unbiasedness, satisfies the unbiasedness. So here I have taken x bar. So you let for generalized case, let our xis follows n theta theta square. So here we can say let our sample estimator is t. So in generalization case, we can say expected value of t equal to theta. So theta can be any population parameter and t is the statistic. So if you don't know the statistic, what is statistic, so you can check the lecture I have given in the link is in the description. So basically t is here I have taken t1 is x bar, t2 is s1 square. So these samples any function is the statistic. So if the expected value of sample statistic gives the parameter value, this is called, this estimator will follow the unbiasedness property. So in many times questions asked to calculate the amount of bias if it is not satisfies the unbiasedness property. So amount of bias can be calculated by amount of bias equal to expected value of t minus theta. It is the this gives the amount of bias if not satisfy the unbiasedness property. Okay, so that's all about the unbiasedness property. So here you can take another concept as if expected value of t greater than theta, then t is positively biased, and expected value of t is less than theta, then t is negatively biased. So here we can take a very small example about unbiasedness. So here I have taken a very small example regarding unbiasedness. So let x1 up to xn is a random sample from a population with normal following normal distribution with mean mu and variance is 1. So we have to show that t, the estimator of sample estimator 1 by n summation small xi square. So this is the function of these sample values is an unbiased estimate of the mu square plus 1. So here our aim is what? So according to definition, expected value of the statistics gives us, if gives us the parameter population parameter, then we can say the estimator as unbiased. So our aim is to prove that expected value of t, that is expected value of 1 by n summation xi rho square, that is given to us, will follow mu square plus 1. So now how to do that? So in proof we have expected value t equal to expected value of 1 by n summation I equal to 1 to n xi square, so equal to 1 by n. So you can know this is a constant term, this can be outside of the expectation, and summation can be outside I equal to 1 to n expected value xi square. So since I will return it here as we can summation xi square equal to expected value x1 square plus dot 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 plus xn square small n square equal to expected value x1 square plus up to plus x expected value xn square equal to summation expected value xi square I equal to 1 to small n. So now uh, here we have data x1 is to xn be random sample from population with mean mu and variance is 1. So here we have given expected value xi equal to mu and variance of xi equal to 1. So we need expected value of xi square. So how to do that? So we know the variance formula in the expectation form as expected value xi square minus expected value xi whole square equal to 1 is given to us. So expected value xi square equal to 1 plus expected value of xi whole square. So here we can get expected value of xi as mu given to us. So this is mu square. So expected value of xi square equal to 1 plus mu square. So we can put this value in this equation. So expected value of our estimator t equal to 1 by n summation I equal to 1 to n 1 plus mu square. So since this is a constant term, so n can be multiplied like this 1 by n into 1 plus mu square. So if we cancel this gives us 1 plus mu square. So here we get expected value of our statistic t equals to 1 plus mu square, which is given in the question. So that t equal to 1 by n summation xi square is an unbiased estimate of mu square plus 1. So we prove it as expected value of t equal to 1 plus mu square. So this proved. Now the second property of estimation theory is consistency. So first of all the question comes, what is consistency? So we have previously defined, let t be a statistic. So we can say the t as a consistent estimator if Tn converges in probability to population parameter theta as n tends to infinity. So n is what? N is sample size. Tn is what? Is our statistic. So what does it tell us? When we increase our sample size, our estimated value will as close to the true population value. This is true population. So a good estimator's another property is if we increase that estimator's sample size, it will close to the true population value. So that is all about the consistency. So if an estimator is given to us and we need to find it's consistent or not, so we can use this formula for practical purpose, that is expected value of that estimator is tends to gamma theta, uh, that is the population value as n tends to infinity, and the variance of that estimator will tends to 0 as n tends to infinity. So I can say this is the very important property. You have to remember this for the practical purpose. So now we'll take a numerical example based on consistency. So here we have a question. Prove that sampling from a normal distribution with mean mu and variance sigma square, sample mean x bar is a consistent estimator of mu. So here we have let xi be our random sample which follows the normal distribution with mean mu and variance sigma square. So we know the sample mean x bar will follow the normal distribution with mean mu and variance sigma square by n. So this you can get from the large sample theory. If xi the sample value x follows our normal distribution with mean mu variance sigma square, then its mean, that is x bar, will follow the normal distribution with mean mu and sigma square by n. So here we get expected value of x bar as mu and variance of x bar as sigma square by n. So if we take as n tends to infinity, so expected value of x bar will be mu, and as we take as n tends to infinity in variance of x bar, so we'll get what? Variance of x bar equal to sigma square divided by infinity, which can be tends to 0, because some number divided by infinite will tends to 0 always. So this satisfies this property of consistency. So we can say x bar is a consistent estimator of population parameter mu. So this is a practical example. So now we'll take another example. So here is the another example. So xi with our sample values I equal to 1 to n is the independent and identically distributed Bernoulli from Bernoulli population with the parameter 1 and theta. This is the support of our distribution. So you know the support of any distribution is its length that given to us. Then as an estimator of theta t x1 x2 xn equal to this function is given to us. This is also I equal to small n is the each dash. So we have to check the consistency. So this is the sample function. From the sample values we calculate this. So we need to check it follows the property of consistency or not. So first we have given xi follows Bernoulli distribution with 1 and theta. So here we have given estimator is based on this x1 x2 up to xn. So here we can say summation xi will follow the binomial distribution with parameter n and theta, because Bernoulli is based on only one trial, but binomial for the n trial of Bernoulli variate will follow the binomial variate with parameter n and theta. So here the expected value of summation xi will be n theta, and variance of summation xi will be n theta into 1 minus theta. So now we have to check this consistency. So expected value of t equal to expected value of summation xi plus root n divided by 2 divided by n plus root n equal to what? 1 by n plus root n is constant outside. So now we'll write expected value summation xi plus this is also a constant value. Right, we can write this root n. Now expected value summation xi we have computed here as n theta plus root n divided by 2 equal to, if I solve this becomes 2n theta plus root n divided by 2 n plus root n. So this will not equal to theta. So this is not what? This is not unbiased, we can say. Here we are not given to check the unbiased, but we can write it's not unbiased. Now the question we have to take as n tends to infinity. So we can solve this as expected value t equal to 2n theta divided by 2n plus root n plus root n divided by 2n plus root n equal to I can write this like this as n plus root n to n plus root n. So now if I write this as 1 plus 1 by root n plus I can take this at numerator as 1 by 2 root 10 plus 1. So if now if as n tends to infinity, this term becomes 0 and this whole term becomes 0, so we end up like only theta as n tends to infinite. So this satisfies the consistency property as expected value of t equal to theta, true population value. Now the variance of t. So variance of t is variance of summation xi plus root 10 divided by 2 n plus root n. So the constant term will be outside 1 by n plus root n square. So variance of summation xi is n theta into 1 minus theta plus this is 0. So now I can write this as theta 1 minus theta divided by n plus root n whole square divided by just take this n to the denominator of this term. So this is theta into 1 minus theta divided, I can square like this as 2n root 10 plus n divided by n equal to theta 1 minus theta divided by n plus 2 root 10 plus 1. So now as n tends to infinite, so this whole denominator will be infinite, so theta into 1 minus theta divided by infinite. So this will tends to 0 as n tends to infinity. So our expected value of t tends to gamma theta, that is theta, and the variance of t tends to 0 as n tends to infinity. Here also as n tends to infinity. So this satisfy our consistency property. So the estimator t equal to summation xi plus root n divided by 2 divided by n plus root n is consistent but not unbiased. So here one remark you can write like this as a consistent estimator need not be unbiased. So this is an important concept. Now the second concept about the consistent estimator is we can get a consistent estimator by using method of maximum likelihood. This is the most important concept of consistency. If a probability distribution is given to us, let a probability distribution like xi follows normal distribution is given to you and asked you to calculate the its consistent estimator. So how we can calculate this? The steps we can follow to calculate it. You have first you have to write the PDF, write the fx, then you have to calculate the likelihood function, that is L is product of fxi, that is you have to product fx1 into fx2 fxn. This will give you the likelihood function. Now in third step you have to take the log of likelihood function. this will written as summation I equal to 1 to n log of fxi. Now in fourth step you have to calculate the maximum likelihood estimator and equate it to 0. Now you can get theta cap as your MLE estimator, and this estimator will always be a consistent estimator. So this is one of the method of getting a consistent estimator by using method of maximum likelihood estimate.